and I want to talk about how we can make Postgres faster using just-in-time compilation. And one thing to note is that while I work at the moment for Enterprise DB, a significant part of this work has been done while I was still working for Citus Data, so I think they deserve some co-credit. So the primary motivation for working on just-in-time compilation is performance, as most of you might have guessed. Oh crap, is this not working? Okay. And so just for an example, I'm going to show a profile of a query, and it doesn't really matter specifically which type of query it is. I'm just going to use it as a prop to show performance. This query here is a query from the TPCH performance benchmark set, and it's query 1, and it's basically a simple query. It's just a group by with a lot of aggregates over a simple table, and has a filter about the time frame. And if you look at the profile of this, we are going to see that most of the time is spent in exec interpret expression, and that means we have an expression and we want to evaluate its value. And expressions in this case are things like, hey, what's the value of this column? What's the value of extended price times blah, 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 blah. And so we spent about 35% just in that. And another 10% is roughly spent in slot deform tuple. And slot deform tuple is the function which converts an on-disk tuple into its in-memory representation. And then below that, we're going to see we spend another 10% of the time in sled get some utters, which is just the wrapper for sled deform tuple. So that deforming in total already is 20% of the time. And then below that, we can see that we have here things like float 8 ecum and float 8 plus. Float 8 plus is just adding two floats to each other. BP char EQ is how comparison to char datums and so on. So we can see that in this specific query, nearly all the time is spent in either evaluating expressions or including the operators referenced or in the deforming of the tuple. If you go down a few entries, we're going to see other things matter performance-wise. So the one solution, I worked a lot on making each of these faster. Before Postgres 10, we spent a lot more in the equivalent of what was back then exec interpret expression. I tried a lot to make this faster, but at some point I got stuck. We can't make it faster by just improving the code. We need like a new approach to make things faster. And one approach to do that is using just-in-time compilation. And what is just-in-time compilation? It's converting interpreted code, and interpretation just means that you have like a sort of program in memory that you want to evaluate, but that's not in the native form that your CPU directly understands. So you have to have a program that evaluates that program, which means you like pay some overhead in that double indirection. And that makes things faster in two basic approaches, and a lot of minor things. It allows you to specialize code for specific cases. For example, you have the code that interprets an on-disk tuple into its in-memory representation, but it has to deal with all possible forms of a tuple. You might have a tuple that consists of 1,000 columns. You might have a table that consists of 1,000 columns. You might have a table that consists out of 3 columns. And each of those cases you have to make work. And if you instead are able to specialize that code for your specific table, you can remove all the conditionals that are dependent on the number of columns. You can specialize it so it's correct for a specific type of column and so on. The other way is that you can remove all the overhead of the interpretation. And that often means you can remove a lot of indirect jumps. That is jumps where the jump target is not known at compile time. Instead, it's a runtime determined, and it reduces the number of branches, and so on. I'm going to go into more detailed examples for each of those. And the technology of doing just-in-time compilation is well known from languages like JavaScript in your browser. Your browser doesn't use interpretation for your all the JavaScript you run in your browser. Instead, once it notices that some part is executed frequently, it converts that into native code and executes that. Similar, if you have a hotspot Java VM, for example, it uses just-in-time compilation to convert the Java bytecode into native code when it detects that it's hot. And a lot of other languages. So what methods of just-in-time compilation have I considered? A lot of old databases and a lot of other projects do just-in-time compilation by when they detect that some program, part of the program or query is slow, they just emit a lot of C code. Then they fork a process, invoke the compiler on that C code, which they have generated just by text concatenation. Then that gets linked into a shared object. Then they load that shared object using like the dynamic linker, and then they run that program. That is not exactly the most elegant approach, because you need to fork a compiler, which means you need to have at runtime a compiler installed on your production box. It means that you can't easily do inlining, and you have to do a lot of string building. So I kind of decided very early on that I don't want to go that. But seriously, there's a lot of old school production databases out there that use exactly this approach to do kind of just-in-time compilation to make their queries faster. Another approach, and that's getting actually pretty popular these days, is to just have your just-in-time compiler part of the program directly emit code, like the machine code, into memory, and then remap the page to be executable, because in modern CPUs it's not allowed to be able for a page, for memory location to be writable and executable at the same time for security reasons, so you have to remap it and then run it. But the problem for that is that for directly to emitting machine code, you have to have a lot of knowledge about the individual CPU, and you have to write this translation from your interpreted program into the native language for each specific CPU. So we would have to have a different layer for that, to do that for x86, for x86 64-bit, for ARM 64-bit, and for all the other, I don't know, roughly 12 languages or architectures that Postgres supports. That would be a lot of work. I actually started playing around with that, but more out of curiosity than that I thought it would be a real approach. And it works, but it's too much, like the amount of work needed is too high. It's worthwhile to note that a lot of other projects started using just-in-time compiler frameworks and then went more and more towards building their own framework. Like a lot of the browsers had their own just-in-time compiler framework, then used something like LLVM, and then finally went back to using their own just-in-time compiler framework for performance reasons, but their reasons don't quite apply. Also, they have a lot more resources than we have. So I kind of said this is not a realistic approach for Postgres. So that basically leads to the conclusion that we have to use some external framework which supports, which absolves us for the need to deal with individual architectures and so on. And there's a few out there. The most well-known is probably LLVM, and that's what I decided to do. But before that, I looked at a bunch of other frameworks. One which is actually looking pretty decent is there's a GCC library where you can do just-in-time compilation with GCC. Unfortunately, the licensing is not compatible with Postgres, and it's not very mature because it's only kind of started like a few years ago and it has no real production users. So I had to conclude that's not really an option. I looked at the infrastructure used by JIT, which is also not really feasible in my opinion. So in the end I concluded that we want to be based on LLVM. And at that point I want to have, can you guys tell me, who of you have heard of LLVM? Oh, cool. Who of you have used LLVM like from a programming point of view? Okay, so that's decidedly fewer. Cool. So what is LLVM? It's basically a framework to build various forms of compilers. And while its name used to stand for something like low-level virtual machine, that they just abandoned that, and it's just a compiler framework now. And one of the important things that it has this intermediate representation, IR, and that's basically a high-level assembly language where you can emit a program, and you don't need to know very much about the architecture. You don't need to know which instructions exist. You don't need to know how to encode instructions or anything like that. All that is not represented in there. Instead, it's relatively high level, but it is low level enough that you can give it enough information about how to optimize that program. And you can build a lot of different front ends that generate this intermediate representation. For example, the CLang compiler, which you might have used, which is C compiler, or Swift, or all generate this intermediate representation, and then LLVM internal optimizer can use that code to generate native code. And there's a lot of optimization passes available in LLVM, so it's good that we can take advantage of those. And now we come to the more Postgres-specific part. And unfortunately, there is going to be some low-level details. I hope I roughly got the right balance between a lot of details and enough high-level right, but I'm not quite sure. Postgres, as you might know, is written in C, and most of LLVM is written in C++. LLVM has a C API that exposes a subset of LLVM to C. Unfortunately, it's not quite enough. There's some functionality that's not exposed via the C API that we need for Postgres, or to do JITing in Postgres efficiently. So what my plan there is, or what I've done, is that most of the usage of LLVM in Postgres uses a C API, and then there's this 2 or 3 source files that do use the C++ API and then expose from that another C API that the rest of Postgres then uses to encapsulate all the C++ usage into very few files. And I hope to get most of that at some point merged into LLVM, so we don't have to use any of the C++ stuff. Although I personally do like C++, it's not bad. And what I did was that all the LLVM usage now is in a shared library, so which has the advantage that we don't link the main Postgres binary against LLVM, which is good because LLVM is roughly 50 megabytes, like the library of LLVM is roughly 50 megabytes large. You can get that down to 35, 40 megabytes, but that's still pretty large, and we don't want to force every distribution to install as a hard dependency to have LLVM on a Postgres package which is half that size. So instead, you can put LLVM into a separate package and install that, and because it's a shared library, you can just put the shared library and all its dependencies in, and from then on, it will get used. Another pretty significant part is how we deal with errors and when they occur while LLVM is running, and that's the next one I want to talk about. So unfortunately, LLVM is not necessarily quite tuned to the use case Postgres has, because normally, the original users of LLVM were like a C compiler, and if a C compiler runs into a fatal error, what is it going to do? It's going to print an error message to standard error, return a failure exit code, and done, which doesn't quite work with Postgres. If LLVM, while running, runs out of memory and detects, hey, I want to exit because I don't have enough memory, we don't want to kill the entire Postgres server. Instead, the best case is to just return an error, or we want to limit the scope of the error to individual connections. But if you just exit one from a process somewhere that uses Postgres, and Postgres itself doesn't know why we exit, then Postgres is going to say, hey, something unexpected is happening, going to kill the entire postmaster, restart everything from scratch, and which will kill all connections. We're probably not going to be too happy with that. And unfortunately, LLVM is not exception safe. So even though it uses C++, you can't just say, hey, in that place throw an std out of memory or whatever the exception name is, and then we catch that, because it's an exception safe for some overhead reasons, that doesn't work. So we have to find a workaround that, and I hope LLVM improves the situation around that at some point. whenever Postgres enters LLVM code, we have to install a bunch of fatal handlers that say that gets a callback. It's basically callbacks that occur when there's out-of-memory errors or other fatal errors. And in those, when they occur, then we can just say we promote that error to a fatal error, which Postgres knows to deal with, but then we can't ever re-enter LLVM, because if you were to re-enter LLVM after throwing that error, we would call into something that has the corrupted state, because we might have been in the middle of a function that modifies the state. So that's unfortunately not supported by LLVM, so we have to throw a fatal error which will error out that individual connection, but not the overall server. Which basically means that whenever Postgres interacts with any LLVM code, we will have to enter, before we have to wrap those sections of the code with LLVM enter fatal on out of memory, and once we're done with interacting with LLVM, we'll say LLVM leave fatal on OM. And which means that in that section, when then there is an out-of-memory error, we'll instead kill the session. But note that that's only about the just-in-time compilation. It's not about running the just-in-time compiled functions. That means we're dealing with the out-of-memory situation due to just-in-time compilation, not the one running the functions. So that is not great, but most of the time you're going to have a lot more memory usage in the type of queries that use just-in-time compilation, because that's going to be analytics queries rather than OLTP queries. And most of them use a lot of memory just because you want to have a lot of work memory, so you can build large hash tables in memory and so on, or do sorting in memories that instead of on disk. So it's not actually easy to reproduce this. I only was able to reproduce these with creating joins between tables that have each 1,000 columns, and then join that 100 of them or something, and then you get into a situation where you run into out-of-memory problems. But that's not that realistic, I think. There's another larger and more important category of errors. That is, if you have a query and somebody, for example, cancels the query, or your query tries to do an insert into a table somewhere and a constraint is violated, then that query will also error out. And in that case, we're not inside LLVM, but we might be running one of those functions. But then we also need to deal with the error in a different way. Because if we just errored out and then continued execution, we would leak all the created functions. So in that case, we need to know how to clean those up. But that's not a problem, but in those cases, they're not fatal. We can just error out, say, like the normal error out of memory. And yeah. The API in Postgres to emit just-in-time code is the following. Every time, the first time a query wants to use some just-in-time compilation, and how it decides when to do that, I'll come to in a couple slides. We say, hey, we want to create a context for all the just-in-time compiled code that we have in this query. You could also have another context, for example, for non-query related things. For example, we could, which I have not done, to use just-in-time compilation to make the copy command faster. And then that would create another context, for example. And then once we created that context will be used for the whole query. And whenever we want to emit a function, for example, we want to emit a function, hey, this expression is one function, to evaluate you call it, then we get a module. And a module is basically the LLVM language for a translation unit in C. So one object file, something that will result eventually in one object file. And then we can add a lot of functions to that. And the important part is that when we add functions to the module, we will not compile the module itself. We'll wait to compile it once till we get somebody asked to get the function from the module, and which will just return a function pointer. And in the case until somebody calls LLVM get function, the compilation of the module will be delayed. And that's very important, because typically if you have a query, it will have 10 different expressions there. We don't want to compile each of those individually, because the overhead of compiling is pretty much, is not just related to the size of the number of functions in, but there's a lot of one-off overhead. Like emitting the functions, which I said, you need to do then mmap and then mvmap to say, hey, this is now executable code. That's really constant time. So like batching all the functions together into one invocation of the optimizer and then the code generator is very good. So we'll usually, when we run a query, we'll add a lot of different functions to the same module, and then at execution time, the first time the function gets executed, we'll actually get the function for that. And if any errors happen during the query execution, or if the query successfully ends, then the whole query the whole context gets deallocated in batch, which also saves time. So now we come to the point to understand how does Postgres actually evaluate queries, and that has expressions, and that has changed since Postgres 10. In Postgres 10, we have basically our own mini bytecode language to evaluate expressions. Before that, we had done like some tree traversal of expression trees, and that turned out to be slow. It also had some significant disadvantage of how we can do just-in-time compilation, which is why I changed that to this bytecode representation with the eye, hey, this might be easier to JIT, and it's faster. Basically, if you have an expression that like this one, where a.column smaller than 10 and then a.another column is equals 3, this will result in a number of expression steps. We'll have scan fetch sum, and what that means, we'll have to, like from the scan table, which is the current table that we look at, basically, we need to look at that we have available deformed the value of column and another, and that can, if we do that together, it's faster, so we do that once for the whole expression. Then we need to get the value of that column, then we need to evaluate the value of a constant, which is obviously pretty simple, in this case 10, and then we need to evaluate a function. And the function here is int4lt, because this, we just assume this is an int4, like a 4-byte integer, and int4lt is int4 less than, and that's how this function gets evaluated. Because in Postgres, every single operator is implemented as a function call, because Postgres is very extensible. You can add any sort of data type by just invoking like create function and then create operator, create type, and so on. And so we call that function. And then we call some setup for evaluating the AND. For example, this one might already return false, in which case we do not have to evaluate the second part of the AND, right? Because if it returns false, the whole expression can't be true. So we can jump directly to the end of the expression. And then, if it's true, we have to evaluate the value of this, the value of the 3, and then are those two column values the same? And then we again need to evaluate some AND expression-specific stuff. And it's interesting that most of these, we have like a big function that evaluates this, and this is basically a switch over the opcode, and the opcode is this, then once it's done, it will jump to the next expression, to the next expression, to the next expression. Most of those are unconditional jumps, but there will be indirect jumps, because our evaluation function doesn't know that always after fetch, the next one will be a scan, and so on. Instead, will be, hey, look at an in-memory location, what's the next thing to jump to? And some jumps in here are going to be conditional. For example, the evaluation of the Boolean might say this is false. In that case, you can jump to the end of the AND expression, or it may say true, and then we need to continue evaluation. And for the ones that have written an interpreter before, we currently, if we have enough compiler support, it's a direct threaded interpreter, which is like slightly better and slightly faster, but it's still like a major bottleneck, as we have seen in the profile before. And the important part is there's a lot of indirect jumps in here. We have the indirect jumps from each of those to the next expression, and sometimes you have even conditional indirect jumps. And there, one thing, a short interlude, how does Postgres represent a function call? Because Postgres can have like functions that have like default arguments, you can have functions that have arbitrary numbers of arguments. We can't use like the native C, or we can't easily use the native C representation. Instead, we have our own function call interface, and that basically consists out of that the functions get passed a pointer to a function called info data, and that has some metadata, and then has a two arrays, one of arguments and one of whether these arguments are null. C doesn't have a direct representation of whether a value is null. For most data types it has for pointers, but not, for example, there's no representation of this integer is not initialized. It is a null. So we have an array of booleans that says whether this parameter is null, and the function invocation then just invokes the function pointer that's stored inside the metadata for each function. And then there's a pointer, and then we call that. And you might realize that that means that we have to do a function call with a bunch of parameters. We have to fill in each of the arguments. Then we have to fill in whether the arguments are null. Then we have to reset whether the whole function returns null. Then we call the function. Then we need to check whether the function returned null, and then we're done. That means individual function calls are pretty high overhead. And we'll play a role in a bit. So this is the code how we evaluate a function expression that is strict. We don't need to understand this everything in detail, but there is a number of interesting points here. For one, we have a loop here that loops over all the arguments and checks whether the function has any null arguments, because the strict function will return null if any of its arguments are null. And most of the common operators in Postgres are strict. For example, if you add a null to an integer, we won't actually call the int for add function plus function. We instead will just return null. So we'll have to check whether any of the arguments is null. So we'll have we first have a bunch of memory dereferences to get at the information about the function call from the metadata of the opcode. Then we have to iterate over all the arguments. And note, if we were to compile this code, then we wouldn't have this loop here, because we know that there's only 2 arguments or 7 arguments or 100 arguments. Instead, during interpretations, we know that we have to look this up and have a loop. So all these branches here about the number of arguments are completely unnecessary. Then we need to check for each of the arguments, hey, is this one actually null or not? Those we would even need if the program were compiled, unless the optimizer can prove that the function cannot accept a null argument. Then we need to reset whether the function returns null, then call it, and then we can get at the function return values and save them in some scratch space, and then call the next. And calling the next one will be an indirect jump, because we don't know what the next operator will be. So this is, again, pretty expensive. In the JIT case, instead, we can remove most of those branches, because we know we have exactly 2 arguments, so we can just omit the code for checking each argument. All the indirect function calls, we had here an indirect function call, for example, to call via the address, and if you call via address, that's an indirect function call because it can change at runtime which one we call. We can replace that with a direct function call to the specific function. And that will save us a lot of time. Just turning on just-in-time compilation for the function without any inlining, without JITting the tuple deforming, we'll go, for example, for TPC-HQ1 on my laptop while running a browser. So this is definitely not a scientific benchmark. This is just representation, but the differences are large enough. We'll go from 28 seconds to 22 seconds. And the interesting part is that if you look at the branch misprediction numbers, before the just-in-time compilation, like 0.38% of the branches are mispredicted. And given that a misprediction of a branch has a penalty of over 100 cycles in a lot of cases, that actually is pretty high. And we can see that after just-in-time compilation, only 0.7% of the branches are mispredicted, so we saved a lot of mispredictions, and that is the largest cause of these speedups. And the other interesting part is that if you look at using perf, how many instruction translation side buffer lookups we have, we can see that we are more than roughly 3 orders of magnitude better when we use just-in-time compilation than when not. And that's not a perfect measure, but it roughly shows how local is your code. And this is the generated IR for just the function expression code. You don't have to understand this in detail. I just thought it would be interesting to show the textual representation of some of this IR. And what you can see right now is here is basically the just-in-time compiled version of the C code we saw earlier. We get the pointer to the array of arguments. and I'll come back to that in a second. Then we go to the next block, and this is an unconditional jump. The compiler can optimize that trivially away, and then we check here if we access the first element of the argument null array, load it into memory, compare it to 1, and then say if it's 1, then we jump directly to the next expression, which is the next block. If it's null, if it's not null, then we check for the next argument. And then we do the same thing here, and then here we have the actual function call. And the interesting part is here, we first reset this is null argument, whether the function returns null. And then we can see we have a direct reference to an external function, and that's the, in this case, okay, this is from the TPCH query, not from the where clause I presented earlier. It's just whether a date is smaller than a timestamp. So we don't have an indirect function call here. The compiler knows which function to call, and the generated program will have a direct function call to that. And then we look at the result. But you can see that to do that, we needed to access this function called infodata struct, and we needed to access individual elements in that. And that means that the IR needs to be able to interact with structs that we have defined on the C side, because we need to be able to say, hey, at this part of this, the struct is this element, which means that the LLVM needs to know about the types that we have in Postgres to be able to interpret the code. We could alternatively put in a lot of like constants that says at this offset, then cast the argument, but that would be relatively complicated and overhead and would be slow. So we need to synchronize function types between LLVM and the C code. And the way we can see here, like the function called info, we need to add in the LLVM IR, and we have this offset of 7, for example, to get at the argument array. And the way we have done that is basically we have one C file which does not get linked into the final binary, which lists all the types that LLVM needs to know about, and then we use LLVM, the C-line compiler, to convert that into bit code. Because one of the cool things about C-lang is you don't have to necessarily emit like machine-readable code, executable code. It can also directly emit this LLVM intermediate representation. And that allows then us to use that in the AR. And then we just, at the startup, we reload that file, and then we have the type information available in both places. And the offset, unfortunately, there's LLVM's representation doesn't have field names, so we have to I just added a bunch of defines that say have the offset number that we can then reference in the C code that emits the LLVM IR. That's not pretty, but it's the best I could come up. It would be cooler if LLVM optionally could have field names, because the overhead of that would be purely at compile time. It wouldn't be that bad. Before that, I had manually synced up the types, which obviously is extremely failure prone and a lot of work, and yeah. So we saw already in the profile that we spent roughly 20% of the time doing tuple deforming. So another very important case to just-in-time compile is the tuple deforming, and you can optimize a lot of things away in that case. Because while the tuple deforming code normally needs to be able to deal with any sort of table shape, it can have one column of type integer, it can have 1,000 columns of type text, and so on. So the code is very generic. If you could generate code for a specific type of table, with a specific format, we can remove a lot of these conditional arguments. We know that how many columns there are in the table. We know whether there's a guaranteed number of columns. For example, if this 1,000th column of the table is not null, then we know that at least 1,000 columns exist in the table. Even if somebody later added a column to the table, we know there have to be at least 1,000 if there's a not null column at the end or at some point. We know which columns have which alignment. So by generating the code specific to a specific tuple desk, which is the description of how a tuple looks in Postgres, we can get quite the speed up. Even though afterwards we still have, the deforming is it's still a bottleneck, which is not surprising, because looking at the tuples is going to be, if you have a query that looks at 100 gigabytes of data and all of that is in memory, just assume, then that's going to be the main source of memory accesses. And if you have 100 gigabytes of data, that's obviously never going to fit in your caches. So you can still, later, rewrite how you evaluate queries to be more memory efficient, and there's a lot of potential for that, but it's worthwhile to note that even if after just-in-time compilation, we spend a lot of time in this. And if you just enable the tuple reforming versus like JITting the whole query, but not the tuple reforming, you can see we get from 22 seconds to 19 seconds roughly, and we reduce the number of branches per second from 14,000 million and to 1,100. Even though the whole query took longer, we have less branches per second, which is cool. We saw earlier that the generated query had a lot of still had like function calls to like date LE timestamp or float for accumulative, which is the aggregate code, or float 8 plus or whatever. So all of those are in C code in Postgres. It would be a lot cooler that if we could inline those so we don't have to have external function calls. And because I told you earlier that the function call overhead in Postgres is fairly high because we have this arbitrary number of arguments, we need to know whether they are null, but in a lot of cases the call functions, if you have just a function that adds two integers, we don't care about whether the arguments are null because it's a strict function. So we can optimize we don't need the null array. If the function never can return null, then we don't need this has returned null check. So we want to enable the compile LLVM to optimize all that array. But for that to happen, we need to be able to get at the source code of the function that we call. And luckily, as I mentioned before, CLang can generate IR for functions, for all the Postgres code. So at build time, what I've done is that we generate LLVM IR for all the Postgres code and install that in a server directory, and build like indexes to know in which of those files is the code for that and that function. And then we can, at runtime, if you want to do inlining, can look, hey, we call this function, how large is this function? If it's 10,000 lines, then we don't want to inline it, but if it's below some cutoff, then we want to say, hey, get this inline this definition into the program, and then the compiler might be able to optimize things away. So to enable that, there's a new directory in the back end, which is just /big bitcode, and then inside that you can have per module code. One of the modules will be Postgres, which is just the Postgres code, but because we want to enable like extensions to also use advantage of the just-in-time compilation. So if you have an extension and you install that on the server, it can, like for example, we could possibly have like a Postgres extension that wants to do some JITting. I don't think it will help a lot, but let's just assume that it could install that into Postgres, index.bc, and the individual files in there. And then those could be used for just-in-time compilation. Unfortunately, I couldn't make use of LLVM's inlining logic. LLVM has inlining for cross-module stuff for its link time optimization, but unfortunately that has some requirements of be able to promote the visibility of functions. So if there's a static variable that multiple functions want to see, multiple modules want to see, it can just say, hey, make this, instead of a static variable, rename it into some unique name and make it externally visible. We can't do that because it happens at runtime. We can't recompile Postgres while it's running to just evaluate a query. That wouldn't work. Obviously, that would be way too slow, and you can't replace a running image anyway. So that's not feasible. So I had to write our own inlining logic, and it does uses this index that we have built and builds a combined index over all the extensions that are available, and then checks, hey, there's an external function reference, can we inline the target functions, and then there's some safety checks. How large is the function? If the function is too large, then we don't want to inline, and so on. So how do we, at the moment, at the planned time, decide when to do just-in-time compilation and when not? There's basically a very naive cost-based analysis. We have we have three variables that say if we have JITting, if the query has a cost that is higher than that, then we want to do just-in-time compilation without optimization. If it's then even more expensive above the optimized cost, then we want to do optimization. And if it's even more expensive about the inline, this should be, say, inline cost. If JIT inline cost above inline cost, then it will do inlining. And it will make the decision for the whole query. Instead, in comparison to something like a JavaScript just-in-time compiler, what they do is they have so-called just tracing compilers, which means they will check, hey, how many times has this function been executed? If it's more than 10 times, then it will emit it. I started with that, but it turned out to just be slower because we have something better. We have how expensive is a query, and we can use that as a proxy to decide when to do just-in-time compilation. That works reasonably well. I think I need to still tune about individual values here, and I think at the beginning we'll need to get some field experience. One interesting thing is that if you use just-in-time compilation to do a profile and use normal perf without any support for profiling, you'll get profiles like this where there's a lot of symbols because it doesn't know about all the just-in-time compiled functions. So you need to tell it to add additional information. If you do that, we can get sensible profiles, and then we can see evil expr are the generated JITed function, and in this query there's three of them, or more, but like 3 of them that we can see prominently in the profile. And one interesting part here is that we can see even after just-in-time compilation, which made the query roughly twice as fast, we can still see that we spent the majority of the time still in expression evaluation. And that's largely because the generated code we do is not that great, and I'll come to that. And the other part is that the query just inherently spends most of its time in doing expression evaluation because it's like a large number of aggregates. Yeah, this is just I'll skip over that because of time. So what at the moment is the problem? Why aren't we getting bigger gains? And the main reason for that is that the generated code is pretty crappy. And that's because I want to get the basic feature out instead of spending a lot of time optimizing everything and then never get to the point where you can get extra field experience. And the main problem is that the generated programs reference a lot of memory locations, and the memory locations are per query. So we'll have a lot of references to, hey, they load this pointer from the static memory address that it's hard-coded in the program, and they load that. And unfortunately, LLVM is not very good at doing dead store elimination and so on when it references memory locations that aren't on the stack. If we were to be able to convert the program so they all reference only on stack locations, then LLVM can convert that into its form where it can detect a lot of dead stores and loads, and things get faster. I have prototyped this, and we get roughly another 2x performance benefit from just improving the generated code. The other big thing is that at the moment, because of the same issue with memory locations, all the generated programs have to be done for every single query execution because we reference memory, and the memory is per query memory, so we can't just reuse the program because the pointers in there will point to some freed memory, which obviously will not work well. And it's pretty important that we enable caching at some point because, for example, query 1, if you don't do any optimization, no inlining, it takes 3.5 milliseconds or 4 milliseconds in total to do just-in-time compilation. But if you do enable optimization, then we can see that it takes 180 milliseconds or something in total to do optimization. And that's already quite the fraction for a query that takes 18 seconds or something afterwards. And if you instead accidentally misestimate when just-in-time compilation is beneficial, and you do just-in-time compilation for a more complicated query that takes a second, and just-in-time compilation takes also a second, even though it might be faster to execute afterwards, you will have lost time overall. So caching of that will be very important, but that's not going to happen in Postgres 10. Yeah, and I think that's where I'm going to stop, and if somebody has questions, I'll happily answer them. Do you very much?
Do you get instruction rescheduling, especially across inlining boundaries?
Yes, there is some rescheduling, but there's some parts that limit the benefits because, as I said, some of the things are references to external memory, and LLVM, even if you add annotations about, hey, this memory is lifetime ends after the query, it only begins in the query, unfortunately can't eliminate all the memory references, so the benefits of that are reduced. But once you convert all that external memory references to be allocast local in this function, then memory has, like LLVM converts all that to registers, and then after that it works perfectly, and you can it even eliminates like duplicate overflow checks and stuff. They get done once, it works beautifully, but there's just a lot more work needed to get there.
Well, I have a very strange question. I mean, you did a very cool thing, how you made your company open source it. And this is the first question. And the second, maybe I was not listening not good enough. It's not clear to me, do you have a custom IR emitter for common bytecode instructions, or you took the interpreter implementation in C and just translated it to IR using Slang, whatever, and you're already using it?
How I got my company to do that is twofold. A, there's a lot of customers that say, hey, we want Postgres to be faster, so there's customer demand. And B is that before hiring I said I want to only work in open source. So that was that part, but the second part is I do emit custom, there's C code that emits the IR for the most common instructions, because and directly emits those, because that's a lot faster than doing something else. And for the less common ones, it just calls a function that evaluates that's the same between the interpretation and the non-interpreted version, and then the inliner can pull that in, and then LLVM can, if it decides it's beneficial, to do specialize that function to generate, which then results in basically using C-length code to emit it. But doing that always is too slow. So it's a bit of both. I don't know whether we still have time.
You mentioned the extensions before. How hard would it be for an extension to benefit from this kind of optimization?
It's basically a bunch of makefile rules where you have to add a bunch of makefile targets that say, hey, generate the code and then install it into the server, and then afterwards it works. It'll only benefit if it's like C code that's for the operators. If your functions then call into, I don't know, some external library that you don't have access to, then it won't benefit. But like for the simple cases, and those simple cases are the ones where you benefit most, because then the function call overhead is the biggest part, then that first works.
That's why you said PostGIS.
Yeah, that's why Postgres was a stupid example, because like most PostgIS functions are so expensive and do so much stuff internally that you will not see a huge benefit. But there's, like, if you use, for example, the, I don't know, concept B-tree gist extension, then there it helps a lot more. Cool.
So, for the people leaving, please use this tool.